Let me introduce myself. My name is Hiroshi Hayakawa. I'm a platform engineer working for LY Corporation's private cloud division. And LY Corporation is one of the largest internet companies in Japan and offering a wide variety of services. For example, communication app, internet portals, news media, and e-commerce, and so on. So we have been operating platforms at a large scale for a long time. So I hope to share that experiences as well. And I contribute to CNCF Platform Engineering Community Group. And I have written books on Kubernetes in Japanese. And my top priority of this presentation is to introduce my DIY keyboard to a global audience. I introduced my desk setup on same stage last year, but now I upgraded like this. And I've integrated a trackball into keyboards. Sorry, pretty cool. Yeah. So anyway, today I've divided the agenda into 4 parts. You can see them on this slide. First, I'll explain what a platform is, and I'll talk about its main functions and its basic architecture. Next, I'll introduce several architecture patterns. These patterns are used for internal platforms built on Kubernetes. And I'll also show how each pattern affects a multi-tenant platform. And third, I'll share some best practices for multi-tenant Kubernetes-based IDP. These practices help the platform run smoothly when many teams use it. And finally, I'll wrap up with a short conclusion. I also highlight a few key takeaways. All right, so let's get started with the background. So first, I would like to start by talking about what platform engineering is. To understand it, I think it would be helpful to look back at the trends of recent IT paradigms. For example, DevOps, microservices, and so on. And these topics in the slide have common purpose, which is speeding up the application release cycle. However, on the other hand, they increase the amount of knowledge that developers need to learn and responsibilities they need to take. For example, to put the CI/CD into practice, developers need to learn CI/CD tools like Jenkins or something. And platform engineering addresses this issue. It reduces developers' time for doing such practices by providing an in-house platform. This platform automates non-essential tasks in application development, and it's known as the internal developer platform. So you might think that Kubernetes can also be an IDP in the sense that it reduces non-essential tasks in developing and operating applications. And in fact, Kubernetes can do that. For example, it abstracts underlying computing resources, and applications can be managed declaratively using text files called manifests. And it can also automate restarting, scaling, and updating applications. Furthermore, we can extend Kubernetes to meet our organization's specific requirements. And this slide shows an example of an IDP designed with a focus on providing Kubernetes to developers. Developers access the platform's features through a simple interface. From there, the platform automatically creates a Kubernetes cluster for them. And each cluster comes with add-ons needed to operate Kubernetes and deploy applications. These are pre-installed, so developers don't have to set them up themselves. With this approach, every developer team gets its own Kubernetes cluster. In other words, the platform creates a dedicated cluster for each tenant. And this model also has both pros and cons. One advantage is strong isolation between tenants by creating an individual cluster for each tenant. And isolation helps with security, limits the impact when failures happen, and keeps lifecycle operations from affecting other tenants, for example, upgrading a cluster. There are many benefits that come from this separation. And another advantage is high level of customization. Since each tenant gets its own dedicated cluster, they can customize it freely. For example, they can grant administrative privileges inside their cluster and manage it the way they want. On the downside, operational costs become higher. As the number of clusters grows, managing all of them requires more work and resources. And resource efficiency is also lower because clusters are separated per tenant. We can't consolidate resources across them. And this naturally leads to less efficient resource usage. These disadvantages grow as the number of tenants increases. So in larger organizations, the impact becomes more significant. To address this, we can use a different design approach. So it is multi-tenancy. Multi-tenancy helps reduce cluster management cost and enhance resource efficiency by providing platform capabilities to multiple tenants with fewer Kubernetes clusters. Of course, multi-tenancy is not a silver bullet. It has advantages, but it also comes with downsides. By sharing clusters, we do lose some of the benefits of the dedicated cluster model, such as strong isolation and high configurability. But there are several architectural patterns within multi-tenancy, so it's important to find the balance that fits your organization. There's no single perfect answer, but the best design depends on the needs and priorities of the teams using the platform. So now let's look at some architecture patterns for multi-tenant internal platforms. Each design comes with a different balance of trade-offs. As we go through these patterns, it may be helpful to keep those trade-offs in mind and compare how each approach handles them. And I think there are two major architecture patterns for the Kubernetes-based multi-tenant platform. The first one is using a single large shared cluster. The other is combining multiple clusters but exposing them through one unified API endpoint. From the user's point of view, it looks like a single platform, even though it's backed by several clusters. Here's what the single large cluster approach looks like. We have one big Kubernetes cluster and multiple tenants deploy their applications into that same cluster. And inside this single cluster, we can create boundaries between tenants in a few ways. The simple option is to use standard Kubernetes namespaces. But there is also an open source project called vCluster. With vCluster, the platform still runs one physical cluster, but users experience it as if they use dedicated clusters for them. So it provides a much stronger logical separation than just namespaces. In the multi-cluster model, an example of the architecture looks like this slide. Users access a single control plane cluster to deploy or manage their applications. And a cluster scheduler on the control plane decides which workload cluster will run each application. Behind the control plane, we have multiple workload clusters, and each workload cluster hosts the actual applications for the tenants. And a single workload cluster can run applications from multiple tenants. While control plane cluster can be implemented with Kubernetes plus a custom controller, but there is also a CNCF project called KCP. KCP is an open source project that provides an API server similar to the Kubernetes Kube API server, but with features designed specifically for multi-tenancy. For example, with KCP, you can separate CRDs, custom resource definitions per tenant. In a normal Kubernetes cluster, CRDs are shared across the tenants, but KCP lets each tenant have its own version of CRD and manage its lifecycle independently. So now let's compare the single cluster and the multi-cluster architectures. From an isolation point of view, the multi-cluster model has an advantage because it uses multiple clusters internally, and the system gains natural separation between workloads. And we can use this separation in useful ways. For example, placing certain workloads on dedicated clusters or containing the impact of failures within a single cluster instead of the entire platform. Next one is configurability. How much freedom users have to customize their clusters. In this area, both models are roughly the same. In the end, users access a single multi-tenant API endpoint in both designs, and that shared interface limits how much tenant-specific configuration can be allowed. So neither approach makes it easy to apply highly customized tenant-only settings. Next, let's look at management overhead. In this area, the single cluster model is clearly more favorable. Managing one cluster is naturally more efficient than managing many. With a multi-cluster setup, you need automation to operate dozens of clusters, plus monitoring that spans all of them. This requires more tools, more processes, and more operational expertise. As a result, the management cost becomes much higher in the multi-cluster model. Next is resource efficiency. Here again, the single cluster model performs better. In a multi-cluster setup, each cluster needs some extra capacity reserved for safety. When you multiply that across many clusters, all those unused resources and all those unused resources add up and create a large amount of waste. With a single cluster, all tenants share one resource pool. This allows much better overall utilization. Finally, let's compare scalability. This is about which model can grow more easily when we build a large platform. In this area, neither model is strictly better. Each has different kinds of scalability challenges. For a single cluster model, the usual bottlenecks appear in the etcd of Kube API server or the network layer. So we need to address those limits as the platform grows. With a much cluster model, we can add more Kubernetes clusters before hitting those bottlenecks. Because of that, scaling tends to be more predictable. However, multi-cluster setups bring their own complexity. We need mechanisms to combine multiple clusters into one coherent platform, and that adds operational challenges. So in the end, we can't say that one model is clearly better than the other. I've seen real-world examples of both approaches, and both can work well in practice. Each model comes with different advantages, disadvantages, and types of complexity. So the choice should depend on what your organization needs from the platform and on the skill set of the platform team. And if you want lower operational cost or better resource efficiency, the single cluster model is a good fit. If you want stronger isolation options or more predictable scaling, the multi-cluster model may be more suitable. So we compared only two models today, but tools like vCluster or KCP can change the characteristics of the architecture quite a bit. So when designing a real platform, it's worth reviewing these options as well. So now let's move on to the next section. In this part, I'd like to introduce some best practices for developing and operating multi-tenant Kubernetes-based platforms. There are four main practices I'd like to introduce today. First, use Kubernetes features to separate workloads. And second, protect system components so the platform stays stable. Third, choose the right isolation strategy based on the characteristics of each workload. And finally, handle the tenant context properly. We'll take a closer look at each of these in the following slides. First, let's talk about using Kubernetes features to separate workloads. In both single cluster and multi-cluster architectures, it's common for applications from multiple tenants to run inside the same Kubernetes cluster. Because of that, we need proper workload separation between Kubernetes itself. Kubernetes already provides several features that help with this. Understanding these features and using them effectively is an important best practice. Kubernetes provides several features for workload separation, like the ones listed on this slide. We want to go into deep detail for each feature in this session. but I'd like you to be aware that Kubernetes offers many features for different aspects of isolation. When you build a real platform, it's important to review these features carefully and choose the right ones for your use case. The next practice is protecting the system components. In a multi-tenant platform, if a core system component has trouble, the impact usually spreads to many tenants. To avoid that, we need to protect these components and keep the platform stable and reliable. One Kubernetes feature that helps protect system components is priority class. Priority class lets you assign a priority level to each pod. By giving system components a higher priority, the cluster will keep them running even when resources become tight. This way, if the cluster is under pressure, the system components stay healthy and the platform remains stable. Using priority class in this way is a good practice for multi-tenant environments. And another practice for protecting system components is implementing rate limiting. And here is an example. Imagine you run an agent on each node to collect metrics. That agent gathers metrics from all tenant applications in the same node. If one tenant suddenly emits a huge amount of metrics, the agent may not keep up. It can become unstable, and that instability can affect other tenants as well. With rate limiting, we can cap how many metrics a agent processes from each application. If the volume goes beyond the limit, the agent simply stops accepting additional metrics from that source. This allows the agent to stay healthy and continue serving other tenants without letting one noisy workload degrade the whole platform. The next practice is planning isolation based on the characteristics of each workload. In a multi-tenant platform, some applications naturally affect others more easily. For example, very large workloads or workloads with unusual resource usage patterns can put pressure on the system. For these kinds of workloads, it's helpful to apply special isolation strategies so they don't impact other tenants. In a Kubernetes-based platform, the unit of isolation can be a single node, for example, placing a heavy workload on its own node. And in a multi-cluster architecture, one Kubernetes cluster can serve as an isolation boundary. Kubernetes also lets you control which nodes a workload is scheduled onto. By using these features, you can isolate noisy neighbor applications by placing them on specific nodes. We won't go into the details of these scheduling features, but they are worth exploring when you design your platform. They can be very effective for keeping heavy or unpredictable workloads from affecting other tenants. And on a different note, let me introduce how we use workload isolation in a multi-cluster setup to prevent the noisy neighbor problem. This tree map represents the distribution of resource consumption of individual applications. And as it shows, the distributions tends to be divided into two characteristics. A few applications that consume a large amount of resources and a large number of applications that consume small amount of resources. I believe that this is likely the case in many organizations. And considering such trends, we isolate applications with high resource consumption into dedicated workload clusters because they are more likely to cause noisy neighbor problems. Meanwhile, smaller applications are placed in shared clusters. This approach allows us to isolate only the necessary workloads without sacrificing resource efficiency. This approach is based on the same principles in designing multi-tenant SaaS applications. So if you are interested, please refer to this book. In this book, we can see three concepts for multi-tenant architecture: pool, silo, and tenant context. In the pool model, multiple tenants share resources with isolation happening at the application layer. Silo means each tenant has dedicated resources, providing strong isolation with clear physical boundaries. In our platform, we use a mixed model of pool and silo according to the trends of resource consumption. And tenant context is how we identify which tenant each operation belongs to using tokens or similar markers. Tenant context is so important in the challenges that I will introduce later. And the last practice is about handling the tenant context. If we propagate the tenant context through the platform and even to external systems that integrate with it, we can get the most value out of multi-tenancy. What this means in practice will be easier to understand with a concrete example. So I'll explain the example of matrix pipeline of our platform in the next slide. The basic structure for our matrix pipeline consists of agents running on a Kubernetes cluster, a message queue that faces those agents, and a backend behind it. The backend includes some components such as time series databases and query engines, which store the metrics and allow developers to access them. This slide figures out a pipeline for container resource metrics such as CPU and memory usage. Each agent accesses to the kubelet on the same node to collect metrics, then send to the backend through the message queue. The issue was that the metrics agent couldn't identify the tenant of a container just by looking at the metrics from the kubelet. In other words, the tenant context of the metrics is lost through the agent. Without tenant context, all metrics are stored in a single default tenant, which causes overloading of the default tenant. To address this problem, we implemented an extension to the agent that enables it to identify tenants. With this enhancement, we can keep the tenant context and leverage the backend's multi-tenancy features to distribute the load to each tenant. And now this diagram is a bit different from the previous ones. This represents the pipeline for application-specific metrics. In this diagram, agents collect metrics directly from the exporters inside the application containers. Since the agent cannot dynamically identify the tenant context, each agent is configured to collect metrics only from applications in a fixed tenant. This approach helps prevent overloading the backends by distributing the metrics. However, with this approach, the agent assigned to tenants that contain extremely large applications became unable to handle the volume of metrics. In this case as well, identifying the tenants dynamically from each metric works to solve the issue. We implemented another extension to the agent to enable a single agent to handle metrics from multiple tenants by identifying tenants from each metric. This allows us to switch to deploying the agent as a daemon set because each agent only needs to collect metrics from containers on the same node. Since the agent run as a daemon set, they can naturally scale as the cluster grows. All right, thanks for staying with me. We've now covered all the practices I wanted to introduce today. So let me wrap up with a quick summary. First, we talked about why multi-tenancy matters. As an organization grows and the number of tenants increases, sharing resources through a multi-tenant platform helps keep operations efficient. At the same time, tenant isolation becomes more important. Next, we looked at architecture patterns for multi-tenant platforms. We covered both the single cluster and multi-cluster models, and we discussed their trade-offs. The key point is that the right choice depends on your organization's requirements. Finally, we went through several concrete best practices. There are many techniques you can apply, so feel free to revisit the slides and refer to them when you need to. Yeah, finally, I'd like to express my gratitude for cloud native technologies and the community. In addition to Kubernetes, there are numerous projects that support the success of platform engineering.